Okay, so this is a bit of a follow-up to the 3 blue 1 brown video on vectors. Now that I rewatched it, and it is a little more linear algebra focused than I intended, since this is for a multivariable calculus class. So, for example, one of the things he talked about was that vectors in linear algebra are usually considered, they're always considered arrows. Vectors are considered arrows wherever you are, but in linear algebra, those arrows are considered having their rooted at the origin, having their tails at the origin and pointing out to a point in space. That's actually not how we're going to think of them in multivariable calculus. It's more like the physics way. He mentioned the physics way versus the, versus the mathematician way, versus linear algebra. The physics way, multivariable calculus comes up in physics a lot. So in fact, they're more connected to each other. So in fact, we will use the physics notion of a vector as measuring displacement. So this is the word I use, displacement. It's used in textbooks also. A vector, let me just say it this way, a vector is an arrow measuring relative position. So, because there's no real origin in space, there's no absolute center point of all space except your heart. Your heart is the center. No, but so if I wanted to have the the arrow from point A to point B in space, in 2D or 3D, whatever you want, I could have that, and that we call that V. Look like a V. Let me make a nice sharp V. Okay, so that would be V, and that's really the arrow from A to B is maybe how you would write it, right? Like something like that. So so here, just as an example, let's say we were in the plane. Oh, I can make straight lines. Let's say we're in the plane here. Let's see if I can straighten up. Okay, so now this is not straight enough. It doesn't want you to be straight. Okay, so say we're at the point, I don't know, let's say we're at the point 1, 4. And we want the arrow, the vector from this point to the point maybe 5, -2. Doesn't really look like where 5, -2 is, does it? Pick these points in advance. Maybe 5, -2 is down here or something like that. Okay, and so our vector V is going to be this arrow. And how are we going to describe it? Well, if you think about it, you can sort of see that you go from 1 to 5 in X direction. So the delta X is +4 to get to there. And then you go from 4 down to -2. So the delta Y is -6. And so that's kind of what we're going to do. We're going to say this V here in this example is, I'll just write this kind of in quotation marks. We can take 5, -2 and subtract the point 1, 4. So measuring from the tail minus the head, right? Because if we subtract component wise, 5 - 1 is 4, and -2 - 4 is -6. And that's where we got those from. And maybe one way we would write this, I'll tell you some notations in a moment, but one way we could write this is something like, some books use angle brackets to make it clear it's like an arrow instead of a point in space. And really, if you think about it, what this represents is this is the change in X, and this is the change in Y. Right? And then again, I said something like displacement, right? So in fact, I could draw an arrow, say, from the origin down to the point 4, -6. And that would actually be the same vector as far as we're concerned in multivariable calculus. This is basically the same vector. It's more about relative position. So we can think of picking this up and moving it to here or vice versa. Okay. So that's the first thing I want to say. So yeah, like this was one notation, this angle bracket notation. Let's see, we could also use, well, okay, so before I get into other notations, let me say the following. So the big thing also mentioned, like in the 3 blue 1 brown video, which is really important. In fact, when you abstractify away and ask about like what vectors really are, vectors are things that you can add and scale. That's kind of our mathematical objects. Which you can add, that you can add or scale. So anything that you can add or scale could be considered a vector. Add or scale. And so that's really because, and if you think about it, like in the 3 blue 1 brown video, we saw this way for adding arrows, but you could also add lists of numbers component wise. So let me just say again, the addition works like the following, right? If I'm in the plane here and I've got, for the purposes of illustrating this, I will draw arrows rooted at the origin. They didn't have to be, but it makes it a little bit easier to see. If I have V and say W here, then I can pick up W and move it up here and add tip to tail he was talking about. There's a couple different ways people describe this. So you could think of, so now this new vector in the middle from there to there is called V plus W. And so you can think of this as tip to tail addition by putting the tail of one vector on the tip of the other. Notice it is commutative. If I do V plus W, I get the same thing as W plus V. Also, some people call this the parallelogram law because that's the parallelogram, and then it's kind of ends up being the diagonal of the parallelogram. So you'll also hear this described as the parallelogram law. Okay. And the other thing that's nice, that's really nice, that is shown nicely in the videos, in the 3 blue 1 brown video, is that it's nice that you really can just add component wise. I can add the X components together, I can add the Y components together. If there's 3 dimensions, I can add the Z components together. So that that makes it pretty easy to calculate the sum of 2 vectors. Just add, so it's a funny sounding word, but component wise. Okay. And then scaling is similar. You sort of stretch by a scaling factor C. The vector by a scaling factor. I don't know, C, some people use lambda, we'll use lambda later in the semester. So V becomes CV. And if C was a half, that would mean I'd actually shrink by a factor of a half. It was -2, that means you actually flip it around and point it in the opposite direction and scale it up by 2. So -V is just the vector pointing in the opposite direction. And you can scale these. There are better pictures in the other video, so I'm not going to draw pictures, but you can scale component wise too, which is nice. You can just, if you want to scale a vector, you can just scale the exponent. If I want to double, if I want V to become 2V, I just scale the X coordinate and scale the Y coordinate. Okay. Now back to notations for a minute. This is an important notation that comes down to, actually it comes down to this addition law. It's actually a useful thing, the fact that we can add tip to tail. We can write any vector, some people call it resolving a vector, I think, into components, but we could write any vector in terms of its X, Y, Z components if we're in 3 dimensions. It's supposed to be the word components. I'll write that again. My handwriting with the iPad pencil is very bad. Okay, so yeah, so what do I mean in terms of each components? Let's actually do the 2D version of this first, just to show it. So say I have my axes, my y-axis and my x-axis. And let's say I draw the vector v from the origin out to, I don't know, let's say the point 4, 1. So that's the point 4, 1 right there. We call this vector v. There's these 2 special vectors. So if I think about just length 1 here, is that 1? It's probably too close to be 1. Half, and then so maybe that's 1, and I guess 1 is up here. If that's length 1. Then we have these 2 special vectors. There's this vector that's in the positive x direction. That's just length 1. That just goes from the origin to 1, 0, right? And there's a name for this. People call this I. And similarly, there's a vector in the positive y direction, length 1, that people call j. And then if you think about what v is in terms of I and j, well, I can just, 2, 3, I made it too long now. 2, 3, 4. I'm really just doing 4 i's, right? Pretend these are all the same length. I'm just doing, this is really 4i, this whole thing right here. And then I can just add 1j to it. And so in fact, what we're going to do is we'll write something like the following. We'll write v equals 4i plus j. That's an I. May not look like it, but that's supposed to be an I. So v is 4i plus j. Sometimes I and j are called like, I don't know, the standard basis vectors or just the standard vectors, or there's lots of different names for them. Okay. And so in fact, this is, you can think of this as another notation. You can think of this right here as another notation, but it really is just, it really makes sense in terms of this I and this I and j vectors, right? So like, I'll just put off to the side here, maybe that we can also, we can also say, well, we could also write this in linear algebra, as mentioned in the 3 blue 1 brown video. They write them as vertical columns. You'll do that if you take a linear algebra course, or we could write it with angle brackets. Some textbooks just use angle brackets like this. One other notational thing, sometimes people write I hat, that's supposed to be a hat, I hat and j hat instead of I and j. The hat is any vector, some books for any vector with length 1, which are important. Important vectors I'll talk about in a second. They're called unit vectors. Those are, some books reserve that little hat, this little hat symbol instead of an arrow. I like to draw this little arrow, but some books will use this little hat for like a vector of length 1. I just want to say similarly in 3D, I'm not going to draw it as elaborately, but in 3D we have, like, if the x-axis is in this direction, y-axis is in that direction, and the z-axis is in that direction, and we go out to length 1, maybe on all 3 of these axes, that's length 1, 1, 1, then you have the I vector right here. We have the j vector right there. And this vertical vector is called k. So we have I, j, and k as our 3 basis vectors. And we can build every vector out of these, right? I mean, the point of the plane up here was that we can reach any point in the plane just by moving east, west, and north, south, right? So you can just tell it how far to go in the east, west direction, which is how many i's, and how far to go in the north, south direction, which is how many j's. And you can get to any point in the plane. Similarly, in space, I can just go by some number of i's, some number of j's, some number of k's, and I'll get to some point in space. Okay. And so it's like I said, ijk or I hat I j k or I hat j hat k hat. Some books use like that. I think our book doesn't, just uses the ijk. Okay, so there's just one other thing I want to talk about before I wrap this video up, and that's that there's another important thing to say about vectors, another way to describe them, like when something's a vector, and that's that vectors have both a size, which we use as magnitude. So that's really the length of the arrow, and a direction, the way the arrow points. And this is another way to distinguish arrows from other objects in mathematics. So like other objects in mathematics. So like I could say here, like as opposed to what are called scalars, which you've probably heard that word for just like a constant. You can think of it as a scaling factor. And scalars only have magnitude, no direction. Right, it just has a size. It's basically a size. Magnitude, no direction. So that's an important thing about vectors to consider, is that there's two really important properties to describe a vector, both its magnitude, which is how long it is, and the direction it points. Direction, it is funny. You can talk about direction with angles if you want. Like in 2D, you just need one angle. In 3D, it turns out you can describe a direction with two angles, and we'll talk about that later in the semester. But I don't really describe, some people talk about, like another thing with like the way the word resolving a vector into components is like using the cosine and sine of the angle the vector makes with the positive x-axis in 2 dimensions. But it's funny, so I'm not going to worry with the angle stuff for now. I would more say, so if we have this so if V is, say, let's just give you an example, 2i plus 3j minus 4k. Then I would say the direction of V is in the 2i plus 3j minus 4k direction. Basically, it's like pointing 2 in the x direction, 3 units in the y direction, and -4 units in the z direction. I can't remember. 2 units in the x direction, 3 units in the y direction, -4 units in the z direction. So that's kind of what I would say, right? Like, it's kind of sounds silly and almost self-referential, but that's the point, is like these 3 numbers do describe a unique direction in space. So it's in the direction given by its components. Maybe you could think about like the ratios of any vector pointing in the same direction would have to be like 2 to 3 to -4, right? Like if I double it and said 4 to 6 to -8, that's 4i plus 6j minus 8k. That would be a vector pointing in the same direction because the ratios are the same. Does that make sense? Hopefully. Oh, I did something in backwards order. I meant to say magnitude first. Let me come back to direction in a second. Let me talk about magnitude because that's the simpler thing. So magnitude is just length. And so if this example that I just had up here, the length and the notation that we use that a lot of textbooks use, our textbook uses this. This is a double bar notation. Some books just use a single bar for the length of a vector. But if we had this vector v up here, the magnitude would be the distance from the origin of the length of the arrow is the distance from 0, 0, 0 out to the point 2, -2, 3, -4, right? And we know how to do that. It's just the Pythagorean sort of the 3D Pythagorean distance formula. So it's the square root of 2 squared plus 3 squared plus -4 squared. That's a squared. And if you work that out, you get 13 plus 16, which is 29. So it's a square root of 29. So that's the length. It's just, yeah. So if v is, I mean, you could write a general thing. If v is ai plus b times j plus c times k, then the magnitude, which again is just double bar notation, is the square root of a squared plus b squared plus c squared. So this is just a notation for the length. Okay. And then the reason I'm saying this, I meant to say magnitude first, is because going back to direction now, I mean, magnitude is pretty straightforward. Hopefully the length of a vector is pretty straightforward. But going back to direction, let me just say, if you wanted to express something as pure direction, sort of, I'll just put this in quotes, pure, if you want pure direction, what you can do with the vector is you can actually sort of scale it so the magnitude is 1, right? 1 is like the most basic, you can scale things to length 1, kind of like some people call it normalizing, like you normalize a quantity by scaling it down to length 1. So if you want pure direction, scale the magnitude down to 1. So for example, if we wanted this vector, this example up here, this v, this 2i plus 3j minus 4k, going back to that one, we could call the vector u, which will be for unit vector. We could take v and multiply it, scale it by 1 over its magnitude, like that. And then that is, we found 1 over root 29 times 2i plus 3j minus 4k. And, then you can actually just move in. You could say that's 2 over root 29, right? We can scale component wise. So you could write something like this if you wanted it purely in terms of, if I really wanted it to be all pluses and just with components, it could be something like this. I mean, honestly, I think it looks nicer just to write it like that. But if you really want to think about it as some multiple of I plus some multiple of j plus some multiple of k, you can. And the reason we tend to use u, u stands for unit vector, which is what we call a vector of length 1. So u, again, or u hat. Some books use u hat for vectors of length 1. This is a unit vector, which is a vector of length 1. Okay, so that's kind of the idea. So if you want to express direction purely without worrying about magnitude, you can always scale things to be length 1. As a 2D example, and this will be the last thing I say in this video, another 2D example. If we're in, again, the 2D plane, and here's a point, the point 4, 3. So if we have a vector out to that point, I always use v, but there could be other letters, like let's call it w or something. So w is the whole vector, right, out to this point. What's its magnitude? Magnitude of w is the square root of 4 squared plus 3 squared, which is everyone's favorite Pythagorean triple. You get square root of 25. Oh my God. Let's try that again. square root of 25, which is 5. So that's length 5. In fact, let me move this up here a little bit. Just label the arrow at the top. So this is length 5 right here. This is length 4, and this is length 3. So it comes from that 3, 4, 5 Pythagorean triple. But if we wanted the unit vector in the same direction, it would just be a vector of length 1. So this could be u, and that would be 1/5 of so the vector w really is 4i plus 3j. So that's really like 4/5 I plus 3/5 j. That's another example of a unit vector. Okay, so unit vectors will come up all over the place in multivariable calculus, so it's good to just get used to the idea of scaling down a vector by its magnitude to get a vector of length 1. And I think that's it. So I will stop there.